Okay, so here we have an equation. An equation is an expression that's set equal to some value or another expression. The main point is that there is going to be an equal sign. So that is what separates just pure expressions from equations, okay? So here, this is an expression x plus 4, but then when we set it equal to a value, like 9, we have created an equation. While we are just left with an expression on the left-hand side, we have no idea what x could be, because x could literally be anything at this point. We could plug in 1 or 10 or negative 80. There is no limiting factor on what x needs or could be, because right now it's just an expression. Once we add an equal sign, everything changes. Once we add an equal sign, then we do have, in this case, enough information to pin down an exact value for what x needs to be to make this entire statement true. So x no longer can just be anything. It needs to be something very specific in order to make the left-hand side equal the right-hand side. Okay, so that's the difference between an expression and an equation. You can solve an equation for a particular x. You can't solve an expression because x could be anything, or whatever the variable is in the expression really could be anything. But here, we can solve for it. There are a couple ways to solve for it. One way to solve is a really long method, which we can do in sort of these simpler problems, which is guess and check. So let's pick a number like 3. Okay, 3 plus 4 is 7. No, that doesn't equal 9. 4 plus 4, that doesn't work either. How about 5 plus 4? That works. So x needs to be 5. That's guess and check. Can you imagine that if it was a more difficult, more complex equation, if we guessed and checked, we might be around here for a long time doing that. We got to figure out a faster, more efficient way to do that. Okay, so the faster, more efficient way is known as isolating x, meaning get x completely by itself. On the left-hand side, usually, we like to read from left to right, so let's put it on the left-hand side. And then some value on the right-hand side. And now we just need to figure out what that value is, and we have x equals exactly what our value needs to be. And I know it's 5 in this case, but let's try to form a situation, a method where we don't need to guess and check. So in order to isolate x, we need to get it by itself. Think of this equation, or all equations, kind of as a seesaw, all right, where the equal sign is that fulcrum, where it's the pivot point, and you want to make sure that this side has just as much weight, so to speak, as this side. So let's say we're talking about pounds here. There's 9 pounds on this side, so in order to even out the scale, we're going to have 9 pounds in total on the left-hand side. And what makes 9 pounds in total if x is 5? Okay, so that's sort of the idea that we're going to be using here in terms of this seesaw or this scale. So just like with scales, if you add a certain amount to one side of the scale and you add the same exact quantity to the other side of the scale, it'll still, if it starts out as even, it'll remain even. So I could add, if I wanted to, I could add 100 on this side, as long as I add 100 on this side, okay, and it's still gonna stay even, okay, balanced. So the opposite is also true. If I subtract from both sides, as long as I subtract the same quantities from both sides, it will also remain balanced. So if I wanted to, I could subtract 4 pounds from the left-hand side and 4 pounds from the right-hand side. Well, 4 minus 4 is 0, so that's just left with x. X plus 0 is x, equals, and then let's subtract 4 from 9, and that is 5. Look. That's a very efficient way to isolate x, and we didn't have to guess and check. So even if it was a much more complicated problem, this technique would have also worked, okay? Okay, so when we talk about isolating x, here's an important note to really look at. Do you see that there's no coefficient here in front of x? If there's no coefficient, you can always assume that the coefficient is a positive 1. So 1x is the same thing as x. So we're not concerned if there's a 1 right in front of the x because we consider that completely isolated. Having 1 of something is not making any more of it. So if I was alone on a desert island and there was just one of me, then I'm still pretty isolated, okay? Now, if there were 2 people, all right, if I had a twin on the island or a friend who came over and there's 2 of us, no, I'm not alone anymore. But if there's just one positive me, all alone on an island, I'm isolated, okay? So, in order to have a coefficient in front of a variable when it's isolated, the only coefficient that it could be, if there is any, is a positive 1. Let me show you a situation where we have not completely isolated the variable successfully yet, okay? So let's say that, let's change the numbers a little bit. Let's say this is a 3 and this is a 2, okay? So we're still going to go through sort of our technique of if we do one thing to one side, we have to do the same thing to the other side to keep it equal. We call this the property of equality. The property of equality. This is the principle that whatever I do to one side, I have to do to the other side. Whether I am subtracting from one side, I have to subtract the same amount from the other side. Adding to both sides, it needs to be the same to both sides. Even multiplying, I can multiply one side as long as I multiply the other side by the same value. I can divide one side as long as I divide the other side by the same value, okay? This is known as the property of equality, meaning that I need to treat both sides equally. Okay, now in middle school circles, it's easier to remember this whole long rule's name as the do-do rule. So you can snicker about that if you must. Okay, but whatever you do to one side, you have to do to the other side. It's an easy way to remember. Okay, all right, so let's keep doing that to try to isolate x. So I'm going to subtract 3 from both sides. If you want to think of it as like 3 pounds from each side, that's fine. So I'm left with 2x, and then 9 minus 3 is 6. Have I isolated x? No, I have not isolated x. I'm not trying to find out what 2x is. 2x is 6. I'm just trying to find out what 1x is. So what we need to do is the reverse operation. So what we need to do is called an inverse operation. Okay? Right now, 2 is being multiplied against x. Now, I put the little multiplication dot in there, but it doesn't need to be there. If a coefficient is right in front of a variable, that's the definition of what a coefficient is. They're always being multiplied. So this is just added information, just as a visual, but you're not usually going to see a multiplication. It's just going to be 2x, and you'll just have to know that it's 2 times x. Okay, so what we're trying to do you see that we had an addition symbol here and now we subtracted it? Do you kind of see that we're doing the reverse or the opposite or the sort of the backwards version of whatever operation is here to try to get x isolated? Well, there's an actual name for that. It's called the inverse operation. So you do these inverse operations so that you can completely isolate whatever variable you're trying to find the value of. So we do everything in reverse order. Kind of like when we were doing PEMDAS, which is the orders of our operation, we were working forwards. Now we're doing the PEMDAS orders of operation, but backwards to work back towards and reverse everything up, like play everything, the tape backwards so we can get back to what the original value was. Okay, so we have to undo a lot of things that were done. So right now, what is being done to the x? We're adding 3 to it. We're multiplying the x by 2. So we need to undo all of those operations so we can get it alone. Okay? So what is the inverse operation of addition? Subtraction. So the inverse operation of subtraction is addition. Okay? So how about multiplication? What's the opposite of multiplication? Division. All right, so division and multiplication are inverse operations. So if you want to undo division, you multiply. And if you want to undo multiplication, you divide. All right, so let's do that here. If we want to get the 2 to be split apart and disappear from the x, since it's being multiplied by 2, let's divide by 2. So this fraction symbol means division. And whatever you do to one side, you have to do to the other side, the property of equality or the do rule, however you want to remember it. Okay, so I divided both sides by 2, which I can do that if I treat both sides equally. Now, 2 over 2 cancel out. They cancel out to 1. Anything over itself is 1. So I'm left with 1x, a positive 1x. Remember, if you have 1x, that's the same thing as just having an x. Okay, so if I want, I could even kind of erase these 2, so I just have x by itself. And then let's simplify this. 6 divided by 2 is 3. Okay, so x equals 3. And that's the solution to making this equation balanced. So what does that really mean? What does it mean for x to be a solution? What does it mean for a value to be found for what x needs to be? For us to pinpoint an exact value that x needs to be? It means that we have solved the equation, but I don't want us to just shout out, solving the equation means to find the answer. Well, that's true, but that doesn't really get at the root of what a solution is. So if I ask you, what does a solution mean? Please don't say, it's the answer. Okay, we need to be a little bit more specific for what the answer means. Okay, when it comes to equations, when you find the answer or the solution, what that means is you should be able to take that answer that you find for the value of the of x in this case, or any other variable that we're working with. So we're claiming, our claim is that x equals 3 for this particular situation. So this is how we prove that this really is the true solution. Okay, this is what it means to be a solution. If 3 really is the solution, then that means that we can plug back in for x. We can substitute out, that means to take out or to switch out, like you're substituting at a basketball game or something. One person in, one person out. The x is substituted out, and the 3 that we found, that we're claiming is the true identity of x, we're subbing it into the equation. We're substituting it into the equation. We're replacing it. We're replacing x for its claimed value of 3. Okay? So 2 times x is 2 times 3 plus 3 equals 9. Okay? So let's see if this claimed solution is indeed the true solution, which means that once we plug or substitute or replace this claimed value back in for x and evaluate this, this side right here, we evaluate this side with 3 in for x, we need to then see what the arithmetic boils down to. So 2 times 3 is 6. 6 plus 3 Ah, look, and then 6 plus 3 is 9. So do you see that when we plugged the solution, which happens to be correct, as we showed that it was actually going to work, that the left-hand side then equals the right-hand side. So 3 is the solution because it makes both sides of the equation equal to one another. Balanced. It is the number that makes this equation balanced or this statement true, okay? Another way to put it is that when we plug in or substitute the solution back in, it means a solution is a value that you substitute back into the equation and creates an identity. This is an identity. Identity means when a number is staring at itself. Okay, this is an identity right here. 9 equals 9, okay? 5 equals 5, 10 equals 10. Those are identities. So if you plug a number back in and you get, after you do all the arithmetic, you get an identity of where the left hand and the right hand side are values that are staring at each other, then that is the mark of a true solution, okay? So a solution isn't just an answer, it's the specific value that when plugged back into the original equation ultimately creates an identity. All right, so there's also one more thing that I want to talk about, truly being isolated, okay? So we said that when x is by itself, x equals, I don't know, let's pick another number, 8, that this is truly isolated. And that's true because the only coefficient that you could possibly put there is a positive 1. Okay, but sometimes you'll do all this great work, all this awesome work, and you get down to something that looks like negative x equals 8. And you're tempted to say, okay, that's the answer, 8. That's not the answer because x is not completely isolated. This negative, that's not a positive 1 at all. You could put a 1 here, okay? But that's negative 1 times x. And remember, we said that to be truly isolated, at the very most, it needs to be just 1 or nothing at all. A positive 1 or nothing at all. Here, this is a negative 1. That is not leaving x isolated. So what do we need to do when we get to this point? Well, again, whatever you do to one side, you have to do to the other. So how could I neutralize this negative? How could I make it a positive, actually? So there's 2 ways. So right now, this is negative 1 times x. So let's undo that timesing, that multiplication. So you divide by negative 1. Whatever you do to one side, you have to do to the other. So negative 1 over negative 1. Okay, look at this. Negative 1 divided by negative 1. So when you have 2 negatives and you're dividing them, they actually cancel out to positives. So if I divide negative 1 by negative 1, I get a positive 1, okay? And then if I divide 8 by negative 1, I get negative 8, okay? So while negative x equaled 8, this was not the solution. That negative actually needs to travel over there, okay? And the operation that we do is by dividing by negative 1. Or if you have negative x equals 8, if you want to, you could, instead of dividing both sides by negative 1, you could multiply both sides by negative 1 because negative 1 times negative 1 is positive 1, okay? And negative 1 times 8 is negative 8. So you get to the same way. So if you have a negative x or a negative variable, the way to get rid of that negative is to divide or multiply both sides by a negative 1. All right, so I think that's a good enough start on solving equations and then checking whether your solution is correct by plugging it back in. And I will see you next time.